Hello, my name is Nicholas Weil, and this is my project about reinforcement learning with Unity ML agents for training virtual NPC drivers as well as for autonomous vehicles. So before I actually dive into the specifics about the project, I want to start with a demonstration of what it looks like so far. Uh, to do that, we access ML agents through a Python interface here, and I run it with this code. And you see the Unity logo here. It's running. This uses ML agents and PyTorch with CUDA as a Python backend for implementing reinforcement learning agent behaviors. And then here we have the Unity game engine where I developed a simulation environment to train these virtual agents and define their behaviors with C# scripts. So I'm going to go ahead and play it now. This is going to resume training from my last checkpoint, so you might see the car fall off the track a couple of times, but it's gotten to where it's pretty good at navigating the track. But basically, I created a virtual environment here and then implemented functionality for the car to be able to controlled by the player, so you can play the game. But then also I'm training agents to be able to play the games themselves, have the gameplay itself. And that teaches cars how to drive autonomously. So far, this one is able to navigate the track almost completely without falling off. Some runs are better than other ones. We can also change the view, and so we can see where it's going. And I'm gonna go ahead and minimize that window, but then let you take a closer look at what the agent looks like in the actual scene. So these red lines are sensors. It is basically sensing what is a checkpoint and then what is parts that it would fall off of. And that is used for the agent to make observations. I created this track in Autodesk Maya, which is a 3D computer graphics software, using splines, and then I imported that into the Unity engine. And I set these triggers here, so if the agent comes into contact with these triggers, then it's said that it's fallen off the map, and I give it a penalty. And if it successfully goes through these triggers here along the course in the correct order, these are checkpoints, then it gets a reward. And so that's the basis of how I've been training it. So that's the simulation environment setup. So what about the actual agent behavior? So the agent here, I've attached several C# scripts to it. Race agent is the most important one. Race agent implements a reinforcement learning agent. And the way it works is that it basically subscribes to the checkpoint system. The checkpoint system detects whether or not the player is driving through the correct checkpoints. So this is more game programming stuff rather than the AI. It just uses Unity's trigger functionality to determine whether it collides with the checkpoint. The race agent detects whether or not the checkpoint is correct, and if the agent collides with the correct checkpoint, then it is given a reward. So +1, if it hits the wrong checkpoint, if this event is triggered, then it is punished with negative rewards. This is an episode reset, so once the agent falls off the track, then the episode resets here. And this is if it falls off of the track, then it loses rewards here, and the episode ends, and then the agent respawns back at the start. And then once the episode begins, the driver velocity is set to 0, so that's in my driver controller. This basically controls the physics of the virtual car. And this is just using basic kinematic equations, like final velocity equals initial velocity plus acceleration times time. And there's support for braking as well, vehicle movements and turns, and it's controlled through inputs. So the inputs could either be set by the human or by the agent. We also collect observations, so the agent is able to observe the environment and collect data, and that lets the AI make decisions on actions. So the main observation that I have is the direction of the checkpoint. We want to make sure the AI is facing the direction of the checkpoint. So that's what it's observing using its sensors. And then these are the actual actions that the agent can undertake. So the agent could accelerate or brake. It could also turn. So it could turn left, turn right, or just go straight. And so the agent will make its decision about its inputs and then pass that to the driver controller. Alternatively, we can control it ourselves if we are playing the game, and so that's using the heuristic function. And so to accelerate, I use Fire 1, Fire 2 buttons. Uh, I'm using a PlayStation 4 USB controller. So the PlayStation 4 controller has the square button, which is for Fire 1, and that's going forward. Fire 2 is the X button, and that's for braking, so it slows down. And then turning is the horizontal axis. These are just Unity functions for accessing buttons on controllers. And this just controls the values that are sent to the driver controller. And finally, the thing that I was showing earlier, if it falls off the track, then it loses its rewards, and then the episode ends. So that's the code that implements the agent. We also saw the driver controller and the checkpoint system. Those are the main three scripts, and they are attached to this NPC character. And then we have some parameters that we can tune. The most important is determining the behavior type. If you use heuristic only, then you get control over the agent yourself, so you can play the game. So for example, I press play. Oops, controller's not so good. So for example, if I press the square button, then we're gonna go forwards. If I press the X button, then I'm gonna brake. And I can try to turn here with one hand. That controls the behavior. And if we fall off, the episode resets. What else do we have? So we can also load a model. So we're training one when when this video first started. So I could add that here, and then instead of retraining it, it's just going to be playing that over and over again. And rate perception sensor, that is what these lines are. It's a sensor just showing what the vehicle can see. And it's specifically looking for checkpoints and walls, and the walls are, again, the parts that would be it falling off. There's also the demonstration recorder, and that is how I did imitation learning. I recorded a demo by pressing record, then I play the game with the heuristic mode, then I switch it back to inference mode, and then it'll try to learn from my demo using a combination of Gale and behavioral cloning. And I think those are the last things that I'm going to talk about real quick. So to specify, we want to use imitation learning. This is the config file for ML agents. You specify your agent name. I called mine race agent. The trainer type, we're using PPO, which is one of the state-of-the-art reinforcement learning models. It's commonly used in robotics, and also the author, I think, tested it a lot on playing Atari games, so it's very well suited for both uh, virtual agents in gaming, and we're doing NPC behaviors here, but also in real life system deployment for robotics, maybe even self-driving cars, which is kind of the area we're focusing on. To add additional imitation learning, so it's already doing extrinsic rewards, and that's going to be my checkpoints and falling off the track. That's what this is where the value comes from here. But if you add Gale and behavioral cloning, then that adds the demo as well that I recorded. It's saved in the project files. It accesses the demo, and Gale basically tries to beat the demo. It introduces a new algorithm, a discriminator, and so basically the AI will be doing actions, and it is going to be trying to fool the discriminator into thinking that its own actions are actually my actions coming from the demo that I recorded. So that's what GALE does, and it stands for Generative Adversarial Imitation Learning. Then behavioral cloning is similar. However, instead of trying to beat the demo, it is just trying to copy the demo. And so that combined is reinforcement learning with an additional layer of imitation learning to help speed up the training time. So if we go again, we can resume from the last checkpoint. And it'll continue going again. I switched back to inference mode. So now the computer has control again. So we're waiting. There we go. So now while it's going on the course, we can actually look at some stats. If I go to TensorBoard, I will do source rl scripts activate, and I spelled it wrong. Log your results. There we go. So we're gonna go here, and it's gonna show the results of training so far. Over time, the cumulative reward is increasing, which is great. Of course, this is taking millions of runs for it to even get up to this point. And policy, so the policy, how the policy has changed over time. And this is just a really neat way to visualize the results of the model. But this is my favorite depiction because it shows how rewards have increased over time, but it's taken a lot of trials to get there. And that's because this task is very complex. Alright, so I'm going to quit TensorBoard. And I'm going to also quit this. It's going to make it all the way around. Yeah, it did actually. Sweet. And so that works. Now, once we're done training, how do we use that model? Well, it happens to save. Where does it save? Right here in the results. So this was my checkpoints agent, and it creates an Onyx file. I'm going to copy that into my assets folder. New brain. These are called brains. Very aptly named. And we can assign that here to our vehicles. And yes, I said vehicles, so they're hidden right now, but I've implemented a couple other agents. They're using the same C# scripts. The nice thing about this is you can train one agent, but apply the same brain to the others, and they'll still all act differently. They also spawn in random locations every time. That was to help with the training, so they're not overfit to a certain trajectory. And before I forget, credit where credit's due. This is where I got the models from. It's models resource. And these are from the video game F-Zero. It's a racing game. So now we have these brains specified, and we are in the inference mode. So when I click play, then they should all be racing. Now keep in mind, they all still have physics, so if they crash into each other, it's not going to be good. They can crash into each other. But our focus was not training them to avoid each other, we were trying to help them stay on track. So it is successful at keeping them on track most of the time. They still can fall off. And there are some physics problems, but overall, I'm very happy with how this has come out. These are starting to be believable NPCs that you could race in a game. Uh, and not just for gaming, but eventually towards advanced driving assistance systems. This could be used for training autonomous vehicles. Now, this is only a couple of hours training. Could train for even more time and probably get even better results. And then trying different tracks. I see taking this into different tracks, testing them on tracks they've never seen before, and there's really a lot of work that can be done here. I did have one other demo I want to show. that I was working on just to get everything tested and configured, trying to test getting these agents to collect these coins, and they figured it out. So the platform turns green if they reach the coin. The coin is like the goal. This was like a preliminary step, just getting them to do goal-seeking behavior. But originally, when they first started, they kept failing. They would go off the platform. But they pick it up very quickly. They've already figured it out, and now it's all green. But it eventually gets better, and it's going now directly to the coin in almost every trial. And so this is reinforcement learning without the imitation learning aspect, because this is a very simple task. The racetrack is a way more complex task, and that's why it calls for imitation learning. So in conclusion, Unity ML Agents provides an excellent platform for investigating, testing, and implementing reinforcement learning agents. It also shows the importance of creating simulated environments for testing autonomous vehicles. Reinforcement learning is a task that is great for a lot of applications like self-driving cars, but the problem with reinforcement learning is you need trial and error to develop these systems. But you can't do trial and error in real life with self-driving cars because that's very dangerous and expensive. So using a simulated environment, you can create your own environment in Unreal, like what I did, to create your rewards and punishments, and then you can test in a safe, scalable way. And it's also really cool, really fun to implement. And not to mention the applications in advancing gaming technology as well, implementing game NPCs as well as real-life systems that can be deployed on the road. So that about does it. Thank you so much for watching and for a great semester.